Okay, hello everyone. Welcome to the lecture, and please confirm that you can see my screen and hear me clearly. Okay, thank you. Thank you for the confirmation. So last time we were talking about what? We were talking about the I/O ports, and what we learned is like there on at least on ATmega 328P microcontroller which we are using in the lab, there are three ports, port B, C, and D. Port B and D both are eight. Both of them have 8 pins. Port C has 7 physical pins on the microcontroller, and other than that, we learned that to program or to read and write data from each port, you need to know the working of three registers, which are like three registers specific are associated with each port, and those registers are data direction register, port register, and pin register. And after that, we had a look at couple of examples about how to write the assembly language program to read the data from the ports or write data to the ports, right? So, okay. So today we will have one more example of that, and then we will move over. Then we also will cover some couple of more instructions, and then we move to new topic, which is about jump instruction and the call instruction. Okay. So let's start with an example. So in this example, we assume that an LED is connected to each pin of the port B. Remember, port D is 8-bit wide, right? So we have connected 8 LEDs, and we want to write a program which turns on the each LED from pin D0 to pin D7 in sequence. So we basically want to see that LED connected to pin D0 is switched on. Then after some delay, the LED connected to pin D1 is switched on or turned on, and then after some delay, LED connected to pin D2 and so on, right? So we assume that we also have a function available, which we are naming as delay. So we can simply call that function to insert the delay between switching off of two consecutive LEDs, right? So since this is a new lecture and maybe you don't remember how to program it, so I'm directly going to the solution instead of asking you to do it, right? So for that, what you need to do first is that you need to configure pin D, port D in the output mode, right? So, and even before that, we are using the directive equate to equate the name of register DDRD with its IO address, and same thing we are doing for the port D register. We are using the equate directive to set the name of port D to equal to its address, right? Then we are loading 0xFF in register R20, and we are moving the value of R20 into the DDRD register using the out instruction, right? So now we have configured port D in the output mode, right? After that, what we want to do is that we don't want to switch on all the LEDs at once. We want to first switch on only the LED that is connected with the uh, pin PD0. So for that, we can use the instruction set IO bit, right? Remember, we covered this instruction in the last lecture. So here we can say that, okay, now set the bit at index 0 of register port D equal to 1. So when it will be set equal to 1, it's mean that a high voltage will be driven or will be provided on this output line, and as a result, this LED will glow or it will be turned on. So after that, we are putting some delay, right? So we're calling the function and which will actually waste some cycles. And after that, we are writing another instruction, which actually is exactly same instruction as we have written here, right? Set IO bit, but only difference is that we are changing the index of the register bit that we want to set to 1, and this is the in bit 1, right? So we can do the same thing in sequence, and once the sequence is completed at the end, all of the LEDs will be glowing. Okay. So basically in this example, we just wanted to do the practice of how to use the SBI instruction, a set IO bit instruction. Okay, guys, I don't know, as you know, maybe this is Ramadan. I just need to break my fast. Give me 2 minutes and I will be back. Okay. Okay, I'm back. So the next instructions that we are going to cover in context of IO port programming are uh, skip if bit in IO register is cleared, right? So this is indicated by the acronym SBIC. Skip if the IO bit is cleared. So what is the syntax? So first you write the abbreviation or acronym or mnemonics, whatever you want to name it, of the instruction, and then the name of the register, and after comma the index of the bit, right? So what does this instruction do? So the it performs the following job. It will test the bit whose index you have provided of the given register, and if the value of that bit is equal to 0, then then we are telling the microcontroller to not execute the next instruction in sequence. Okay, so this is like the template. So it is again a 2-byte instruction. So 8 bits are used for the opcode, and 5 bits are used to specify your register, and 3 bits to specify a bit within the register. Okay, so here is an example. So for example, let's say we have this code snippet. So in this code, what we are in the first instruction, what we are saying check the value of uh, bit zero or bit zero in the register port D, and if that bit is cleared, which means if the value of that bit is equal to 0, then skip the next instruction. What is the next instruction? Increment R20. So if the value of the bit 0 of port D is equal to 0, then don't execute the next instruction and directly go to the instruction after the next one, which is third instruction in our sequence. Okay. Is it clear to everyone how this instruction works? It just skips the next instruction in the sequence if the bit at the given index of a given register is equal to is equal to 0. We have a complementary instruction which is named which is named as SBIC. So it is like skip if bit in IO register is set. Previously we were saying skip if the next instruction if the bit in the IO register is cleared, but here we are testing it for the value of 1. So syntax is again same as not same similar. You just need to first write the name of the operation SBIS or instruction, and then specify the register, and after the comma you specify the index of the bit that you want to if the bit index that you want to test. So how it works, it will test the bit at the given index of the given register for a value of 1, and if the value of that bit is equal to 1, the next instruction in the sequence will be skipped. Again, here is the template. So you have like 6-bit, sorry, 8-bit opcode, and then you have 5-bit reserved to specify the register, IO register, and 3 bits to specify a bit within that register. So here is an example. So in this code snippet, what we are doing is that we want to test the value of bit zero in of register port D, and if the value of that bit is equal to 1, then the next instruction in the sequence will not be will be skipped, and the control will come directly to the third instruction. But if the value of the bit 0 in port D is not 1 but is 0, then the next instruction that will be executed is increment R20, and then after that, the third instruction will be executed. Okay. So it is like also a kind of jump, but the range of jump, like it is also a kind of branch. Like the behavior is similar to the branch instruction, but the range of branching is very limited. It is just one instruction. So if the condition is true, only one instruction is skipped. Okay, so here we are going to write a program to understand how we can use these instructions. So we want to write a program which performs the following things. It keeps monitoring the pin PB2, which is the second pin or pin 2 on the port B, right? So it keeps monitoring this pin until it becomes high. So which mean that we are treating this pin as input pin, right? And we want our program to continuously monitor the input value on that pin, and when the input value of the on that pin becomes high, logic 1, then we want to do something. What we want to do? So when the value becomes high, we want to write a value of 45 and dollar mean hexa. So hexa 45 on the port C, right? Which means that port C is configured as output port. And also we want to send a high to low pulse on the pin port D3, right? So which means that we are also using the pin 3 of port D as output, but whole of the port C is used as output. But in the case of port D, only pin 3 is configured in the output mode. So if a high is detected on PB2, we want to send a high to low pass on the PD3. So initially we need to set it high, but initially we need to set high, and when we select that there is a high on the PB2, then on PD3 we make the value low, right? So this is like, I don't know, logic 1 and logic 0. Okay, do you guys want to give it a try before I show you the solution? I think it's a good idea. At least I want you to try at least, so that you at least you start your thought process how to do the example, right? So go ahead and try to do it on your notebooks, and you have 2 minutes to do that. Okay. Is there a question? What does it mean to send a high to low pass? So high to low pass mean that, uh, and remember in this example, you on the PD3, what you will do that at the start of your program, you need to send a high signal. High mean write one, okay? Write one on the PD3 at the start of your program, and then start monitoring the PB2, right? So when PB2 you detected that PB2 is high and the condition is true, then you need to do two things. One, write 45 to port C, and then write 0 to port PD3. Is it clear? Okay, good. Now go ahead and give it a try. You have 2 minutes. Okay, so it's fine if you have not completed, because I just wanted to give you a time to try it. So let me walk you through the solution, right? So first, what we need to do, we need to make PB2 an input, right? Because we are going to monitor it, but not the whole port B, only pin 2 of the port B. How we can do that? For that, we have now this instruction clear the IO bit, right? So we are saying, okay, clear the bit only the bit number 2 of the DDR-B register, which means only pin B2 will be configured as input. All other mode of all other pins on the port B will remain unaffected, right? Now since we are using it as input pin, so we also want to enable its pull-up register. And if you remember from the previous lecture, how we can enable the pull-up register by writing a value of 1 in the uh, port B register, right? But we want to enable the pull-up register only for pin 2 on the port B. And how we can do that? By using the SBI set IO bit, right? Set IO bit uh, at the index 2 of port B, right? So now we have enabled the pull-up register. The next thing is that we need to make the port C an output port, right? So for that, we are first loading 0xFF into R16, right? And then we are saying write R16 to DDRC. So all the pins of the port C will be configured in the output mode. Okay. So another thing we need to do is that we need to configure PD3 in the output mode, only the pin 3 on the port D, right? So for that, once again, we are using the SBI instruction, set the IO bit at the index 3 of the DDR-D register, right? Okay, now we are doing these things like sending high to low. So initially we are sending high on the port PD3, right? So for that we are only we are setting the bit 3 of port D equal to 1. So now if you connect an LED on the pin 3 of the port D, you will see that the LED is glown, right? Uh, but then after that, what we need to do, we need to monitor the value of PB2, right? And here is how we monitor it and keep monitoring as long as it doesn't becomes high, right? So keep checking it, right? So how can we do this? So we are saying, okay, so skip uh, the next instruction if the IO bit is set. So uh, so if the IO bit is set, so we are saying skip the next instruction. So what we want to do is the following: check the PB2 pin, right? And if it is one, then go and do this job. Write 45 to port C and send a low signal on the PD3. But if it is not equal to 1, then check it again, right? So here we are saying skip the next instruction if the bit 2 of pin B register is set equal to 1, right? And what is next instruction? Next instruction is relative jump to again, which is basically saying say go back to the same instruction, right? So what we are effectively what we are saying is that uh, pin is uh, if the pin is set to 1, then skip this the next instruction, don't execute this one. But if it is not set equal to 1, then this instruction will be executed, and which means that control will go back to the same instruction, right? Now if the pin is set equal to 1, it's mean that this RJMP again instruction will be skipped. So if it will be skipped, then what we are doing, we are saying, okay, write 0x45 in R16, which is the value we want to send to the port C. And then we are saying send R16 to the port C through the out instruction. So we are done with this part, sending the value of 45 hex to port C. The other thing we need to do is to generate this low signal, or we need to send 0. So for that, what we can do is that we can use the CBI instruction, clear the IO bit, right? So we are simply saying clear the bit number 3 of the port D register, right? And once we are done with that, we can stay here in an infinite loop. Okay. Any questions? Is it clear to everyone? Okay. So if clear, then let's have another example. So in this example, we assume that a switch is connected to the pin PB0 here, right? So this is the switch which is connected, right? A switch is connected to the pin PB0 and an LED to the pin B7 here, right? So we want to write a program which gets the status of the switch and send it to the LED, which means that if the switch is pressed, this LED should be switched on, and if the switch is not pressed, so the LED should be switched off, right? So how we can do that? Again, let me give you 2 minutes to give it a try. Again, you need to use the you need to monitor the PB0 pin, right? And how you will monitor that pin? By using, for example, uh, SBIS instruction, right? Or you can also use SPIC, up to you. Give it a try, think about how you can encode it, and it's fine if you are not done with the complete program in 2 minutes, but I want you to try to work through it, okay? So go ahead and you have 2 minutes. Okay, so let me walk you through the uh, code. So first thing is that we need to configure PB0 in input mode, right? But only the single pin, the pin number 0 of port B, right? So how we can do that? By using the clear IO bit instruction. So we are using that instruction to set 0 in bit 0 of the DDR-B register. So now our PB0 is configured as input. The other thing we need to do is that we need to configure PB7 as the output, right? So for that, we can use set IO bit instruction by stating that set the bit number 7 of the DDR-B equal to 1. Then the next thing we are doing is that we need to monitor the switch, right? So here we are saying that uh, skip the next instruction if the zeroth bit of pin B. Why zeroth bit? Because remember we configured PB0 as the zeroth pin of the port B as input. So the value which will be read on the input pin will go to the zeroth bit of pin B register, right? So we are saying like if the zeroth bit of the pin B register is clear, then skip the next instruction, right? So when we have 0 here, we also want to send 0 on the LED to the LED, right? So let's say we have the input of 0, which means the switch is not which mean that which mean that the switch is pressed, right? When the switch will be pressed, then it will be connected with the ground, right? So if the switch is pressed, then uh, we need to send 0, right? So uh, so if the switch is so if the value is clear, if the bit is clear, then it's mean that switch was pressed. So the next instruction will be not executed, it will be skipped, right? So if it is skipped, what we need to do is that we need to send now 0 to the uh, bit number 7 of port B register. So we are saying, okay, now clear the IO bit in the at the index 7 of the port B register, right? We are done. And then we need to again monitor the switch. So that's why we are saying go and jump back to again and again start monitoring it. Now this time, let's say that the value which we receive on the pin B is 1. 1 because the switch is open. So if switch is open, the voltage is coming from this side. So this is high voltage. So you get a value of 1 on the input, right? So if the value is high and now this condition is not true, so the next instruction will not be skipped. So the next instruction will be executed, which is saying jump to hour. So hour is another label here. So when we reach here, so we need to now send 1 to the LED, right? So we are saying set the IO bit at index 7 of the port B register. So which mean that 1 will be sent on this line, right? And after that, we are saying, okay, go back and again monitor the input pin PB0. So we are like continuously monitoring, and when we receive 0 on the input, we send 0 to the LED, and when we receive 1 on the input by on the PB0 line, then we send 1 to the PB7. Okay. Any questions? I know it's a little bit tricky using the SBIC and SBIS instructions, but you will get used to it with the practice. Okay. Any questions? No? Okay. If no questions, then we are starting to a new topic, which is about jump and call instructions, right? So what we will cover is, like, as I said, jump instruction, call instruction, and how the stack is involved in execution of the call instructions, and how stack is used when you are calling a function, right? So then we also, not today, but like in the next lecture, we will also talk about how to implement time delays. Okay, so let's first talk about linear program execution. So which mean that if there is no jump, then what happens is the following. Your program is executed in sequence, right? So for example, if you have this program written in the high level language on the right side, so what will happen that first the statement at line number 3 will be executed, then the one on the next line, which is line number 4, and then one on the last line, which is line number 5, and then your program is completed, right? So normally, if there is no jump, no function calling, then your program executes in sequence. All instructions are executed one after the other. However, for practical programs or for a versatile program, CPU must be able to execute an instruction other than the next. So we need to like change or change or modify the execution flow, right? So for that, we need to support the non-linear program execution. For example, we need a conditional instruction to implement the if statements, or we also, for example, some programs require looping or calling a function, right? So how the execution flow works in case of non-linear programs, right? So let's say we have this program written on the right side. Again, it is written in a high level language, not in the assembly. Sorry, guys. So the program on the right side is, as I said, written in a high level language. But the point here is that depending upon the value of the condition, whether the condition is true or false, your execution flow will change. So if we are saying initially A is equal to 2, A is equal to 2, C is equal to 3, and then you are testing the condition if A is equal to 2. So which is not, the condition is false. So the line on the number line on the statement on line 6 is not executed, right? Okay. Again, here's another example, which is basically a loop construct, which again doesn't follow the linear program execution. So first you are setting variable c equal to 0, and then you are entering in the loop body by first setting a equal to 2, and then you are entering the body of the loop. So after three statement line on line 3, 4, and 5 are executed, but after the 5, the next state line that executed is not 6 because you are looping. So the next line that is executed is line number 4, and then 5 again, and then after that 6, right? So it all depends upon the condition. So like these are the examples where examples of the program where linear program execution is not followed. Another example is where you're making the function calls. So for example, let's say you have uh, this program with the main function, which is setting some variables a and a equal to 2 and c equal to 3, and then you are making the function call. So first you execute this line on line number 4, then the line number 5, but when you go to the function call, so then the next statement that will be executed will be line number 8, then line number 9, and once you are done with the execution of the function body, then you go back to the line number 6. So there is no like sequence of execution. It depends like whether you are making a function call or you are implementing a loop or you are doing the if else. So depending upon that, you can deviate from the linear execution of the program. So in AVR assembly, you have two groups of instruction which can carry out the non-linear program execution, right? One of them is jump and the other is the call. So even in jump, you have two subgroups, conditional jumps and unconditional jumps. So for conditional jumps, we have already seen the branching instructions like, for example, branch not equal, branch same or higher, branch lower, right? So branch of carry is set, branch of carry is cleared, and so on. For unconditional jumps, we have instructions jump and R jump, relative jump, and we have a third one which is called indirect jump, not listed here, right? And the second group is function calling, or it is the call functions. So these are the functions like call and return. So we will talk about them later on, but today we will mostly focus on the instructions in the first group. Even in the first group, we will talk only about the unconditional jump because we have already covered the conditional jump instructions or branch instructions. Okay, so in jump, what does the jump instruction do? Uh, so are like all of the instructions in the jump group. So these instructions, they change the program counter. Remember, what is the purpose of the program counter? It holds the address of the next instruction that is supposed to be executed, right? So all of these jump instructions, they modify the content of the program counter, which mean that the they but these instructions actually deviate from the linear program execution because they change the value of the program counter in such a way that it points not to the next instruction in sequence but somewhere else in the program, and which causes the CPU to execute an instruction other than the next instruction in the sequence. As I said earlier, there are two types of jump instruction: unconditional jumps. So these jump instructions, they modify the execution flow unconditionally without checking any condition and directly going to the target location. Examples are RJMP and jump, right? These are two different instructions. We will see what is the difference between them in upcoming slides. The other group is conditional jumps, which go to the target address only if a given condition is true, right? So if the condition is true, then it jumps to the target location. Otherwise, it executes the next instruction in the sequence. And then an example is branch if carry is clear. I think all of you should be clear about conditional jump instructions by this time point, right? Because I guess we had two lectures at least covering the branch instructions. Okay, so first let's see how we can write a program which involves a jump instruction. So as I said, there are three instructions in the group: relative jump, jump, and indirect jump. So when you want to use any of these three instructions in your program, what you need to do is that you need to put a label in your program And how you identify the label? So it is always followed by a colon. Okay. So you put a label next to the instruction where you want to jump. So, okay. And then you attach that label to a jump instruction. So when that jump instruction will be executed, after that CPU will jump to the labeled location or target of the jump. So here is an example. So initially the instruction at the location 3 as line 3 will be executed, right? After that you go to the in sequence you go to the next instruction, which is instruction number 4, but instruction number 4 is a relative jump L1, right? So what will happen? There is no condition checking. Always it will go back to the label L1. So in actually you are here doing an infinite loop. So it will go to the instruction which is identified by label L1, which is the instruction at location 3, right? So this will end up you will end up having an infinite loop. Any questions? No? Okay. So remember we said that the jump instructions they modify the content of the program counter, right? Now these three instructions, jump, RJMP, and indirect jump, they differ in the way how the value of the program counter is updated. In case of jump program counter, the new value of the program counter is specified in the instruction itself, right? In the form of label. In case of relative jump, uh, the you go to the new location. Our new location is like relative to the current value of PC, right? Just like in branches, remember in branch where how you set the new value, it was PC is equal to PC plus 1 plus K, right? So same is here. The new value is set equal to PC plus 1 plus operand, which was K in K when we were discussing the branch instructions. But the difference is that in branches we were updating the PC only when the condition was true. But here in our jump, you will always update the value, right? But the value will be the new value will be relative to the older value, right? In case of jump, the new value is absolute, right? It is not relative to the older value of the PC. And in indirect jump, the okay, one more thing. In both jump and dodge jump, operand is like part of the instruction itself, right? You will see how it is part of the instruction in just like give me 1 or 2 minutes. And after that, I will show you. In case of I jump or indirect jump, the new value of the PC, you need to first specify or put it in the Z register, and after that you call the I jump. So when you will call the I jump, the value of the Z register will be copied into the program counter. Okay, and this basically helps as a pointer. We will see how it is useful. Okay. In case of jump instruction, so as we said in the previous slide, PC is set equal to operand. So how the instruction itself is 4 byte long. Okay, so these bits which are shown in the red color, they are reserved for the opcode, and the opcode is fixed, and all other bits they are used to hold the destination address of the target, right? So these bits, there are in total 22 bits available to specify the address of the target address or target instruction, right? So yeah, so that address can range from 0 to uh, 3 and then 5Fs. So that is the range, like that is the range of 22 bits unsigned number. Okay. So for example, here in this binary form, the target address is 110. Okay, because all other bits are zeros, and these red bits are anyway for the opcode. They are not used to specify the target address. Okay, now let's see through a simulation that how jump instruction updates the program counter, right? So first remember that operand is basically the destination address of the instruction where we want to jump to, right? Uh, so initially our PC is equal to 0, right? And So we will start execution from this point. The other thing that I want to highlight is that we have one jump instruction here, which is at PC value at address 2, right? And its opcode will be equal to 9, sorry, its machine code will be 940C and then all 3 zeros and 6, right? So this is opcode, blue one is the opcode and operand is 6. So basically you are saying that go to the instruction which is located at address 6, okay? And here you have another jump instruction, and the machine code of this jump instruction is 9406 940C, and then the operand, which is basically again the target address, which is 6. And how I know this? Because I'm using label name, right? And what is the address of the instruction to which I have attached the label? That is 6, right? So that's why I know that operand is 6. Okay. So how it works? So let's say the first instruction is executed, and after that the PC is incremented to 1, which means that now the second instruction, load immediate R17.5 will be executed, right? So when it is executed, after that your PC will be incremented to 2, and now we are at the first jump instruction, right? So when you are at the first jump instruction, what will happen? That your PC will be your operand will be copied into the PC, right? Remember, after 2, what we were expecting that the PC is incremented. If there is normally what will happen in sequential execution, that after PC is equal to 2, in next iteration PC or next instruction PC is equal to 3. But here, since we executed the jump instruction, right? So the operand is copied into the program counter. Okay. And one more thing, if you notice here, the first instruction is at address 0, second is address 1, third is at address 2, fourth is and after 2 there is no, like, the next one is not at address 3, the next one is at address 4. Why? Because jump instruction, it is a 2 byte it takes 2 bytes. So is it supposed to take 2 bytes? Let me go to the previous. Yeah, so it is supposed to take 8 bytes, right? 4 bytes. Why it is taking here 2 bytes only? So there must be some mistake, right, in the addressing, because the jump instruction is 4 bytes in size, right? Or maybe this addressing is just not realistic. The addressing here used is only to illustrate the example, but not the actual addresses. Okay, so don't be worried about that. So the point here is like the jump instruction will simply cause the destination address to be copied into the PC, and this is the way how the PC is updated. After that, the next instruction that will be executed is the one at address 6, right? So which is add R16 R17. After that, PC is incremented by 1. So now we are at the next instruction, which is again a jump, right? So when this instruction will be executed again, the destination address will be copied into the PC, which again is the same address 6, right? And then we we will be, so we are again at the same instruction here. So it is like we are doing an infinite loop every time, going back, like, and doing it forever. Okay. Any questions? Okay, if no instruction, no questions, then next instruction is relative jump. Now, the difference from the jump is that, as I said earlier, that jump has in jump you provide the absolute address where you want to go, right? So you have 22 bits to specify that. But in the relative jump, the jump is like how far from the far, like in forward direction or backward direction you want to go with respect to current value of the, with respect to the PC plus 1, right? So in this case, you have 12 bits available to specify the specify the jump or amount of to specify the operand or jump amount of the jump, right? So if you have 12 bits, the range of the 12-bit signed number is -2048 to 2047, which means that relative to PC plus 1, you can go forward 2047 locations or you can go back 2048 locations. Okay. So PC plus 1 is the address of the instructions right after the R jump instruction in the program. So PC is the, remember, PC is the address of the R jump instruction. PC plus 1 is the address of the instruction immediately after the R jump. To that address of that instruction, you add the operand, right? So for example, if you have, let's say this is the machine code of the R jump instruction, then the operand is 110, right? So which means that you are going forward 6 locations from PC plus 1. Okay, now here we have an example simulation to see that how PC is updated in case of our jump, right? So first we have the instruction PC set equal to 0. So the first instruction is executed. Then after that PC is incremented to 1. So next instruction the sequence is executed. After that PC is incremented to 2. And now we are at the R jump instruction, right? So now since we are in the R jump instruction, so when we will jump, what will happen? That what is the label name? So label name is here. It is pointing to the instruction at address 5, right? So we need to set PC equal to what? PC plus 1 plus operand, right? Yeah. So if you noticed it, let me do it again for you. So PC is initially equal to 2, then 5 will be added to it. So 3 is incremented, right? And then to it you add 2. So 2 is like displacement, how much displacement you need to reach the target, right? So this was PC. PC plus 1 is what? The next instruction in the sequence. And to PC plus 1, you add the displacement, amount of displacement needed to reach the target. So what is the displacement needed from 3 so that you can reach 5? It is 2, right? So you add 2 to it, just to show you again. Okay. So that is the new value of the program counter. And now we are at address 5. So this instruction will be executed and then the PC is incremented to 6 and next instruction the sequence will be executed, which is again R jump, relative jump, and you will do the same thing with the only difference is that this time the displacement will be negative, right? Now what is PC? PC is equal to 6, right? And what is PC plus 1? PC plus 1 will be 7. I'm not writing PC plus 1, I'm writing only 7, right? Now you need to go back to 5. So what you need to add to 7? -2, right? So that you can go back to the address 5 because label is pointing to address 5. Okay. So you can see here. So PC plus 1 is 7 and then to it you add -2, which is FFFE. So you come up with the value of 5. Is there a question? So the arithmetic to find the difference between the two code addresses done automatically. Yeah, that is true. That is true. So, but in the exam or in the quizzes, we can ask you, okay, if let's say you have R jump label name, then I can ask you, okay, what will be the value of displacement? Depending, and then you can find it depending where is the label. Is it forward or backward in the program? But like in real life, the hardware does it on its own. You are not supposed to find the displacement. That is only for your understand to improve your understanding of how things works. Okay, the next instruction we have is indirect jump. So in case of the indirect jump, what happens that like the similarity with the jump and RJump is that it also modifies the program counter. The difference is how it modifies the difference is in the way how it modifies the program counter. So here, when you execute this instruction, whatever current value you have in Z register is copied into the program counter. And what is Z register? It is basically combination of R30 and R31. So Z is a 16-bit register. Okay. So this instruction has no operand, but it is understood that whatever value is in the Z register will be copied into the PC on the execution of this instruction. So PC is loaded with the content of Z register. For example, if Z points to location 100, so by executing IJump or indirect jump, the CPU will jump to the location 100 and whatever instruction is at the location 100 will be executed next. Okay. So uh, how many of you know what are the function pointers in our higher level languages? Let me not say how many of you know. Uh, is everyone familiar with the idea of the function pointers? If not, let me know. Is there anyone who doesn't know what is a function pointer? So that if you don't know, I will not use it to explain the purpose of or the benefit of using IJump instruction. Okay. Since no one is saying that I'm not familiar with the idea of the function pointer, I'm assuming everyone knows what is a function pointer. And now the thing is like using this IJump instruction, you can implement the function pointers, right? So what are the function pointers? Function pointers are like just a variable or a pointer which holds the address of a function in higher level languages, right? So for example, let's say if the name of that pointer variable is, let's say, PTR, right? Pointer. And initially, let's say you put in this the address of function f1, right? So when you will now make a call using this function pointer, function 1 will be executed. Now let's say later in your program somewhere you update this pointer variable to point to function 2, right? So, and then when you make the function call using the same using the same pointer variable, the function 2 will be executed. So, which function is executed the depends upon the value contained in the pointer, right? The address of the function whose value is contained in the pointer. So you can implement now the function pointer using the IJump instruction, right? So it is similar, like you can replace this pointer with Z, right? So in initially, let's say in Z, you put the address of the instruction, first instruction in the function F1, right? And then you can say, okay, jump to IJump. So now your function 1 will be executed. And then when you are done with the function 1, you can update Z equal to F2, that which means basically the address of the first instruction in the body of the function 2, and then call again IJump. So now the next function will be executed, right? So it gives you the flexibility, right? It allows you to jump anywhere in your whole address range. It is not like jump instruction where you can use only 22 bits. So you are like kind of you can you can provide only the absolute address, right? But you cannot update your address dynamically in your program, right? So if I want you to take back, where is the jump instruction? Yeah, here, for example, jump label name, right? So every time the same, you will go to the same, or even for example here, jump label name. Every time you will go back to the same instruction, right? But if you are using IJump and in every iteration here you are modifying Z, right? So you will be going to the different address depending upon what you have placed in the Z before using the IJump instruction. Okay. So, any questions before I go to the next topic, which is about call instruction or function calling? No? Okay. So we are going to now start the new topic, which is about function calling. We will discuss first the stack. What is a stack? What are the push and pop operations on a stack data structure? How you can make the function calls in the assembly, and also if you are using the functions or you want to call a function which takes parameter, how you can pass parameters to those functions, right? I don't think we will be able to cover all of that today, but let's see. Whatever we can cover is fine. Okay. So what is a stack? So stack is a data structure which in so let me first explain uh, what is a queue. In queue, what happens is that you have from one side you put the data into the data structure, and from the other side of the queue you retrieve the data from the data structure, right? So for example, you insert the data uh, at the tail side of the queue, right? And you retrieve the data from the front side. So whatever enters into the queue first is retrieved first. So first out, first in, first out. It follows first in, first out principle. FIFO. Okay. In, in contrast to FIFO, you have a data structure which follows the principle of last in, first out. The data structure, which is the value or the data item which is inserted in the data structure last, is the one to be retrieved first, right? So it is just like a stack of, for example, plates in a restaurant. And let's say you have like multiple plates, right? And whenever a customer comes, he will first get the plate which is on the top of the stack, and that plate was placed on the stack in the last was placed in the like last order. That was the last one to be placed on the stack. The plate which was placed first in the stack is at the bottom and will be the last one to be retrieved from the stack, right? So this is the same principle used in the stack data structure. So in AVR microcontroller, for example, at Mega 328P, your stack, so let's say you have a stack structure starting from on one end, it has the lowest address is 0x7FF, and it grows in this direction, right? So it grows towards the lower addresses. So the bottom of the stack, the first location in the stack is at the address 0x7FF. And as you keep putting more items on the stack grows upward. And when we say upward, it's mean that it grows towards the lower or smaller addresses. Okay. And then you also keep a stack pointer or a SP, which basically tells you that what is the current top of the stack, because current top, the purpose of the current top of the stack is to identify the location where you can put the next item, right? So if now SP is pointing to this particular point here, and I want to insert and place a new element or data item on the stack, let's say X, it will be placed here. And after placing, S will be incremented and it will be pointing to the next empty location. Now let's say after that, if I want to place another element Y, it will be placed here, and then SP will be not incremented, decremented to point to the next location, because in AVR microcontroller the stack grows from higher address to the lower addresses, and this is known as stack growing downward. So it is like, how to say, not compatible. Saying that stack is growing downward is not compatible with this our figure, because it shows like the highest address in the bottom and the smallest address at the top. But the point what I'm trying to say, or what the point I'm trying to make, is that address of the next empty location is smaller than the previous filled location. Okay. So SP, it always points to the next empty location, and it is known as stack pointer. Empty location in stack, not in stack pointer. Okay. And stack pointer is initialized by default in is not by default. You have to initialize. You have to initialize it to the largest address, which is 0x7ff, and it points to the larger address in the 2 kilobyte SRAM of AVR. Uh, and The global variables, for example, when you are making a, if you know how functions are written in higher level languages, let's say for example Java, and you know the concept or idea of the global variables, then the global variables are the variables which are visible to all the functions in your program, right? So those global variables, they are allocated from the smallest address, which is 0x100, right? So when stack is too low, it can override global data. So if you like keep putting the elements in stack, and what will happen that you will keep filling the stack. So let on this side you have the global variables, right? GV. So if stack keep growing up, like to the smaller addresses, so what happens that finally it will start over when you will say push put more element on the stack, so it will override the global variables. So as a programmer, you need to be like aware of this issue with the stack, because in you don't have operating system to take care of this issue for you in your microcontroller. Okay, so the stack pointer itself is a, let me just quickly erase it. So stack pointer in microcontroller at Mega 328P is a 16-bit register, right? And which is like actually consisted of two individual 8-bit register, stack pointer low and stack pointer high. So you can actually write the values into these registers, or you can read the values from these registers. So these registers together, stack pointer low and stack pointer high together, make the stack pointer, because you need 16 bits. Why? Because all the instructions are at least uh, 16-bit in their size in the at Mega 328P microcontroller. Okay, 16 bits mean 2 bytes. Okay, so and this is remember SPH and SPL. They are they have their they are in the IO address range. So their IO address is 0x3E for SPH and 0x3D for SPL. But they also have an address in the memory range, which is 0x5E and 0x5D, respectively, for SPH and SPL. Okay. Any questions at this time point? Okay. So if no questions, then let me stop here, because I guess you guys have quiz today. So go ahead and do your quiz. I am available online until the end of the lecture time. If you have any question before that, let me know. Okay. You can send me a chat in the text box. But for now, go ahead and do your quiz.